Have you ever popped open a broken remote control or maybe pulled the side panel off an old desktop PC and just been instantly overwhelmed? It's usually a chaotic spaghetti of messy physical wires and colorful, oddly shaped components. It looks like absolute chaos. But have you ever wondered how engineers actually write all that electricity down? Like, how do they manage to take that physical, three-dimensional mess and translate it into a clean, universal written language that anyone in the world can read?
Well, welcome to this explainer. Today, we are cracking the Rosetta Stone of circuits. We're going to dive right in and learn the basic alphabet of electronic circuit diagrams. By the end of our time together, what might look to you right now like intimidating, alien hieroglyphics is going to reveal itself as an incredibly logical, highly intuitive, and frankly genius visual shorthand. I promise you'll never look at a motherboard the same way again.
Okay, here's our roadmap for today. First, the language of electronics. Second, the zigzags of resistance. Third, direction and light. Fourth, coils and parallel plates. And finally, number 5, the unseen power forces. Let's jump right into it. Section 1. The language of electronics. First things first, why do we even need a translation guide for this stuff to begin with?
Just look at the stark contrast here between physical reality and schematics. In the real physical world, electronic components are, well, they're clunky. They come in wildly different sizes, they're wrapped in plastics and ceramics, covered in colored bands and manufacturer logos. Just imagine for a second trying to draw a complex circuit by hand, sketching every single plastic casing and matching every colored stripe. It'd take weeks to draw a simple radio and the blueprint would be a total mess. Engineers need something fast, precise, and universally readable, whether you're in Tokyo or Toronto. Enter the circuit symbol. It's totally minimalist, heavily standardized, and drawn purely in black and white. It strips away all that physical noise so you can focus entirely on one thing: function.
Moving on to Section 2, the zigzags of resistance. Let's take a look at the components acting as the brakes in our electrical system.
Here we have the real-world items. Up top is your standard physical resistor. It's a tiny, beige ceramic cylinder painted with specific colored bands that tell engineers its exact resistance value. Down below is a variable resistor. It's a much chunkier component, got 3 metal pins, and a large turnable dial. If you've ever turned a volume knob on an old stereo or dimmed a dining room light, you were twisting a variable resistor. They're highly textured, very distinct objects when you hold them in your hand.
But look at how we put this exact same concept on paper. The zigzag symbol perfectly captures what the component does. It's literally a drawing of a difficult resisting path. Think about it. If you're a tiny electron sprinting down a perfectly smooth copper wire, and suddenly you're forced to navigate this jagged back-and-forth obstacle course, you're going to lose energy and slow down. That zigzag instantly tells anyone reading the schematic, hey, electrical current gets restricted right here.
Now watch how this visual language logically builds on itself. You start with that basic zigzag line for your standard resistor. To turn it into a variable resistor, you simply add a diagonal arrow striking right through it. In this schematic shorthand, an arrow passing diagonally through a component is the universal modifier for adjustable. It gives you the exact same functional info as seeing that big volume knob on the real thing, all with one simple, quick stroke of a pen.
Section 3. Direction and light. Next up, we explore the components that force energy down one-way streets and those that give off light. Check out the physical diode here. It's a very small, unobtrusive black cylinder with a silver stripe painted on one end to indicate its polarity. Right sitting beneath it is something you've probably seen a million times in your life, the classic red LED, or light-emitting diode. It's that familiar, translucent red plastic bulb with the 2 metal legs protruding out. The exact thing that tells you your TV is on standby.
What's absolutely fascinating to me here is how the diode symbol acts like a literal play button for electricity. It's a solid black triangle pointing straight into a flat vertical line. This is the ultimate one-way street sign for current. The triangle clearly shows the allowed direction of flow, and that vertical line, it acts as a solid brick wall. It means electricity absolutely cannot flow backward. If it tries, it gets blocked. It's incredibly elegant visual logic that instantly communicates a complex physical law.
And just like we saw with the resistor, we can modify this base symbol to communicate new functions. By taking that exact one-way street sign, the diode, and just adding 2 small arrows shooting outward, we instantly translate it into an LED. Those outward-pointing arrows perfectly represent photons, particles of light, radiating out into the room. It tells you immediately, and without a single word, this is a one-way valve, and oh yeah, it also glows. All right, Section 4, coils and parallel plates. We are leaving the metaphors behind now and looking at symbols that are essentially direct architectural blueprints of the components themselves. Take a look at the physical capacitor, that taller black cylinder you see here.
If you squint closely at the label on its side, you can actually read its exact technical specs: 470 microfarads and 25 volts. Beside it is the inductor. Unlike the capacitor, this one doesn't hide its workings inside a plastic shell. It is quite literally just a tightly wound coil of exposed copper wire wrapped around a core.
For these particular components, the secret to decoding them isn't a clever metaphor like a play button or an obstacle course, it's direct physical mapping. The schematic symbol is literally just a drawing of exactly what the component looks like on the inside. See how the inductor symbol is just a series of looping semicircles? It perfectly matches that physical coiled copper wire. And the capacitor? It is just two parallel lines. Why? Because if you took a saw and cut that little black cylinder open, you'd find exactly that: two parallel conductive plates separated by a tiny microscopic gap. The symbol even includes a positive and negative marker on those plates, so you wire it up in the correct orientation to avoid, well, a small explosion. You are quite literally drawing the physics of the component. Finally, Section 5, the unseen power forces. Now that we have all our individual components laid out and understood, it's time to breathe some life into this circuit and safely ground it.
Now you'll notice these three vital items: the DC supply, the AC supply, and Earth, commonly known as ground, don't have physical photos attached to them. There are no tangible, clunky objects to show you here. You can't just run down to the hardware store and buy a bucket of ground or a standalone alternating current, right? That's because these are unseen forces or broader systemic concepts. Rather than singular physical objects you can hold in your hand, they're represented by pure, clean geometry. The DC supply, providing that steady, direct current from a battery, is a simple, bold circle containing a plus and minus. The AC supply, the alternating current coming out of your wall outlet, is a circle with a sine wave inside it, visually showing how the power literally oscillates back and forth. And Earth, or ground? It's a vertical line dropping down into a series of horizontally decreasing lines, the perfect visual of electrical energy safely dissipating down into the Earth. It is pure, clean geometry representing invisible system forces. So let's lock in this new alphabet. We've taken messy physical reality and perfectly translated it into neat, standardized symbols. We have resistance acting as our brakes with jagged zigzags. Direction, our traffic cops, shown by that rigid one-way triangle and line. We have storage components mapped directly by parallel lines and physical coils. And finally, power and grounding, defined elegantly by pure geometry.
You now hold the keys to a completely invisible language that literally powers the modern world. The next time you pop open a broken device and see a green circuit board or glance at a complex technical blueprint, you won't just see intimidating hieroglyphics, you'll see a clear, logical story. So the question is, which piece of this invisible language are you going to decode first?